Right, so last but not least, we have Simone Speziale, who's going to talk about generalized angular momentum and twistors.
Thank you very much. So it's a real pleasure to be here for this beautiful conference, and it's also even bigger pleasure to be the last speaker, because that gives me the honor as the last speaker of taking this opportunity to thank again all the organizers of the conference for the excellent work that they've done, and to wish you a great continuation for the rest of the program. So Roger, Maciek, Michael, Lionel, Katarina, and David, thank you again. Thank you very, very much. I will be, with respect to this morning talk, disappointing both physics and geometry. Well, certainly this talk will be very much about physics, negligible mathematics, negligible geometry, so I apologize in advance for that. And it will be based on work that you can find in papers with Antoine Rignon-Bray and with Abhay Ashtekar from this year. To give you the main broad context for this work, this context is the beautiful but thorny topic of observables in general relativity. Usually observables are meant to be gauge invariant. In GR, gauge is diffeomorphism invariance, and that immediately makes things complicated because scalars are not diffeomorphism invariant, and so the construction of observables becomes much more intricate. Of course, you can look at global quantities, like the integral of the total curvature, or relative quantities like the scalar curvature at the tip of my finger as opposed to at the point x. But the approach to observables that we'll be interested in is actually one that is based on the notion of asymptotic flatness. So this notion was introduced a long time ago, first in a coordinate-dependent way by Bondi and Sachs, and then in a very elegant and geometric way by Roger Penrose. And it has found a very important ground of application in physics in the context of describing an isolated gravitational system. So the way it works is that typically you imagine to have some interesting gravitational dynamics going on, like coalescing black holes, and their spacetime is highly curved, and the description is very complicated. But imagine that if you are far enough away from the source, then spacetime becomes asymptotically flat, and that gives you access to the standard notion of inertial observers. And then you can use this notion of inertial observers to formulate observable quantities such as mass, angular momentum. And in particular, one of the most important formulas in the application to gravitational waves of quantum gravity, of general relativity, sorry about that, is the Bondi mass formula. And the Bondi mass formula relates the loss of energy of a gravitational system with the energy that has been taken away by gravitational waves. And this formula here can be understood as an application of Nether theorem, which becomes possible thanks to this notion of asymptotic observers at infinity. So the goal of my talk is I have two goals. So first, I would like to expose some of the features that allow you to understand these flux balance laws as a realization of Nether theorem, and especially the role the twistor theory played in clarifying one of the most important questions in this field, which had to do with angular momentum. And then also discuss some of the extensions, particularly one of the standard BMS symmetries that are interested in recent research, and what are the difficulty with making these ideas work. So first part, just basic stuff about Nether theorem and the surface charges application in gravity. And the most elegant and most convenient formalism in order to discuss the Nether theorem in this context is what is called the covariant phase space, in which you start from a Lagrangian, you look at the variations, you get the equations of motions up to a boundary term. You look closely at this boundary term, and you realize that it has the structure of a PDQ term, so it can be used in order to define a symplectic potential. And actually, we are in field theory. This is a four-form, so this is actually symplectic potential current. Then you integrate it on a Cauchy slice to actually get the symplectic potential. Then you take the exterior derivative in field space, and that will give you pre-symplectic two-form, because there are gauge symmetries in this theory. That's why it's not directly symplectic. And so that's the basic object. Now you have the space of solutions of your theory. You equip it with this presymplectic form, and that turns it into a covariant phase space. Covariant because, as you see, you don't need to introduce foliations, no 3+1 split. You can apply to space-like and null hypersurfaces wherever you're pulling back this thing. Even time-like if you want, but then, of course, the initial value problem is not well defined, but in principle, it's perfectly covariant from that point of view. And you can apply to full Cauchy slices or just partial Cauchy slices, which will be the main interest in the rest of this talk.
This is all just signature independent, right?
And it's also signature independent, yes. So, in fact, you don't even need to define the momenta. So, now, as I said, the symplectic potential is a 3-form in space-time, and it's linear in the variations. So you can think of it as being a 1-form in field space. And so this covariant phase space uses a formalism that is called the variational bicomplex, in which you have, I will use notation little d, little I, and pound for the standard exterior calculus in space-time, but then you have equivalence in field space. So I will use delta for the exterior derivative in field space, capital I for the interior product, and this delta xi for the leader derivative in field space. So with this formalism, writing down Nether's theorem is really straightforward. If you have a differentiable symmetry, so the Lagrangian is invariant up to a boundary term, then it's immediate to show that the symplectic potential hooked with the symmetry minus eventually this 3-form in case it is present is closed on shell. And therefore immediately gives you some conservation laws, which are typically described assuming let's say in flat space-time, you have two space-like slices, two Cauchy surfaces. You assume trivial boundary conditions, like the fields going to 0 at infinity, or conservative boundary condition if it's a finite time-like cylinder. And then you get that the total charge here, obtained integrating the current, equals the total charge there, just as a trivial consequence of this. And these are familiar examples of this beautiful theorem. Less familiar examples are the applications to gauge symmetries, local gauge symmetries, because in that case, it turns out that the nether current is actually exact on shell, not just closed. So that means that basically there's no support for the nether charge in the bulk, in this tree surface. All the support for the nether charge is at the boundary. And so in order to see nether charges for local gauge symmetries, you need first of all to have boundaries of your three-dimensional slices, so corners if you want. And second, you need to have a reason to have non-trivial gauge transformations at these corners. Only in that case, you will have non-trivial charges for gauge symmetries and diffeomorphisms. So a case in which this happens, that you have interesting corners and non-trivial allowed diffeomorphisms there, is at infinity. So this is where the contact comes with this modeling of isolated gravitational systems. There are two infinities that are usually considered most commonly. One is spatial infinity, in which, let's say, we use some coordinate system in order to describe this. We send R to infinity at fixed time, or null infinity, in which we send R to infinity but a fixed retarded time. And of course, with this procedure, all the radiation is lost because it just escapes you. But this procedure allows you to capture all the outgoing radiation. And when you apply these procedures to GR, you do find the residual diffeomorphism at the boundary, which in this case are the Poincare group that you would expect as the group of isometries of the asymptotically flat spacetime. At null infinity, you get an infinite generalization of the Poincare group, which is called the BMS group. I would say a little bit more about it later, but it still contains the Poincare group, infinitely many different types of Poincare groups, in fact. But anyways, we are in a setup in which we can apply this Noether theorem because we have non-trivial residual diffeomorphisms. So why people haven't done this already back in the 60s? Well, because there are actually difficulties in applying Noether theorem to this context. And there are two very important difficulties. The first one is ambiguities. You might remember that Noether theorem doesn't give you a unique conserved current. The conserved current is defined up to adding an exact form. For instance, in electromagnetism, you would naively get an electromagnetic stress energy tensor, energy momentum tensor, which is not symmetric, but you can improve it to the symmetric one precisely playing with these ambiguities. This is usually not a big deal, this ambiguity, but in this case, in which the whole content of the current is an exact term, then this ambiguity becomes catastrophic because everything is ambiguous. So that is the first problem. And in the context of the covariant phase space, you can parameterize these ambiguities in terms of cohomology. First of all, as you can see from the definition, the symplectic potential is only defined up to adding an exact three-form in space-time. But also, if you change the Lagrangian adding a boundary term, which does not change the field equations, you will also change the symplectic potential, adding an exact form now in field space. So there's an equivalence class of allowed symplectic potentials, which corresponds to these picking representatives in this cohomology class. Now, for the symplectic two-form, this one does not matter, only this one matters, but for Nether theorem, actually both of them matters. So the first problem is these ambiguities, and the second problem is that usually an immediate consequence also of Nether theorem is that these conserved charges are also the canonical generators of the symmetry, and so sometimes you might fix ambiguities in this way by asking, well, I want that conserved quantity which is also a canonical generator. But there are not even canonical generators in this picture because typically we are describing systems that are open, they're dissipating, radiation is outflowing, we are interested in that case, and therefore the symplectic form between sigma 0 and sigma 1 is not even conserved because of radiation outgoing. And this is easy to see because the property of the symplectic two-form current is to be closed on shell, and so applying Stokes' theorem, you get a formula like this. And so if you have boundary conditions that are conservative, so there's no outgoing flux, symplectic two-form is conserved, then you can define Hamiltonian vector fields and so on and so forth. But if you have leaky boundary conditions, like outgoing gravitational waves, then it's not conserved. And so, in particular, if you have some diffeomorphisms that move this corner, they will be sensitive to the presence of dissipation, and therefore you cannot expect them to correspond to Hamiltonian vector fields. And this expectation is confirmed by a famous calculation that showed that on shell, when you hook the symplectic two-form with a diffeomorphism, well, first of all, you get something that has support only at the corner, which you're happy because it tells you that bulk diffeomorphisms are pure gauge, the general directions in the symplectic two-form, but they might become symmetries at the corner. But also, you get that typically they don't correspond to Hamiltonian vector fields, so this thing is not exact. There is an extra term. This extra term vanishes if psi is tangent to the corner, which makes sense because then you're not moving the corner so that it sees the dissipation, but it's not in the presence of, if you do like a time or retarded time translation. So this is the problem of non-integrability of these charges. So, because, yes?
Is that true for all values of u, or can I give it boundary conditions that you're going to minus infinity so that?
Yeah, this would be for an arbitrary cut. Typically, if you now go to u minus infinity, you would assume no radiativity there. And then if you choose the right symplectic potential, so if you fix the first problem, you will fix also the second problem with a no radiative cuts. So with no radiative boundary conditions at initial and final, it will be fixed. But you have to use the right theta. For instance, I will explain this in a second. If you use the wrong theta, even that won't work. So let me get to that. So because of these problems, this is at the end of the day, people didn't approach constructing charges for the BMS group using Nether theorem because these two problems were hard to solve. So I would like to first make the discussion more concrete with some explicit formulas, which will show you why it's important to choose the right theta, and then briefly review the historical path and how twistors were important there. So if you just do, you open, I don't know, Wald's 84 book, you see that the symplectic potential that you get out of the Einstein-Hilbert Lagrangian gives you as candidate Nether charge a two-form which is known as the Komar two-form. It's just the antisymmetric gradient of the diffeomorphism you are computing. And the surface charge, because it's a two-form, satisfies the following flux balance law. On shell is proportional to T mu nu, the energy momentum tensor of matter, plus something that is proportional to the Killing equation. So if you have isometries, this is actually very useful because that term is not there, and then you get the equivalent of Gauss' theorem in electromagnetism, namely the difference of this charge between two surfaces that enclose a region with matter will tell you the total content of energy due to the matter.
I thought it was a trace problem.
So let's say it's trace free T, trace of T0.
Because you get the
Otherwise you get T bar. Otherwise you get, yes, you get T mu nu minus 1 alpha G mu nu T.
Yeah, because you get the reach tensor.
Yes, absolutely, yes.
Yeah, okay, sorry. Okay. So, but I then can't see how you could get it out of Mercer's theorem.
You don't see how you can get what?
I don't see how you can get Komar out of Mercer's theorem without, or maybe you can...
No, Komar you can. It's just that then you get T mu nu minus 1 half G mu nu T. Truly,
Yeah,
that's what you really
but
get.
then that's wrong. Okay, sorry.
It's a wrong balance law, yes, I agree.
Okay,
This is an example of a wrong, Komar is an example of a wrong flux balance law.
Okay.
But in order to express why, I don't need to, I can assume that conformal matter, trace of T is 0, it will still not be the good flux balance.
But you're saying that you can still do it, there's enough slop in the Mercer argument that you can get it out from the Mercer argument. There's enough freedom in the Mercer argument.
Yes, yeah, absolutely.
So that's the point of what you're saying.
Yes,
yeah.
in fact, actually,
Good.
Penrose's formula, which I will record later on, starts precisely now from T and not T minus 1 half G.
That was really the point, yeah.
That was really the point. Okay, but we'll see it soon.
Okay.
Okay, well, thank you for being this precise. And I was saying, yes, Gauss theorem, so and then once you're outside of matter, you're in vacuum, no matter what shape of surface you use, you get the same value for your charge, which is something that is very nice to have, of course. Now, however, in the general case, which includes as soon as I do this and I produce gravitational waves, there's no more Killing vectors, so we have an extra term like this, and then this flux balance law, on top of having the trace T term, just becomes completely useless. And let me show you explicitly why, for instance, in the case of Scry, future null infinity. So for those of you familiar with the use of Bondi coordinates, that's the parameterization that one uses. If you're not familiar, I'll give you just some physical interpretation about what these symbols mean. You have these Bondi coordinates in which u is retarded time, and θ and phi coordinates on a sphere. The sphere can be taken to be round, and then this r is just 2, this is a scalar curvature. And then you parameterize, it's just a convenient parameterization for the fall-off behavior of the metric. To give it some flavor, Scry is reached in these coordinates at r that goes to infinity, and then you are basically parameterizing Scry using affine coordinates, of which u is an affine coordinate, and θ and phi label cross-sections in this affine parameterization. If you're in Minkowski, then all these fall-off terms, you can set them to 0, because first of all, you can take this to be just a round sphere. Then the shear is purely electric. And if the shear is pure electric, you can distinguish good cuts and bad cuts. So you can actually choose good cuts, so that, for instance, this C on your chosen U foliation is just identically 0. And that's just how you recover Minkowski metric in this case. If you do Kerr, then this parameter M in Kerr in retarded Bondi coordinates, this M is the mass, J is the angular momentum, but in a generic radiative spacetimes, you don't know what the good cuts are. You still call M the Bondi energy aspect and J the angular momentum aspects for reasons that I will explain. And actually, if you don't want to use coordinates and you're familiar with the Newman-Penrose language, then these M and J can be related to Newman-Penrose scalars like so. I'll come back to that. Now, in these formulations, then you identify this asymptotic symmetry group, the BMS group, and using these coordinates, you can parameterize it in this way. There's a vertical component along these null directions, whose parameter has one free function on the sphere, so this is time independent. It has only a linear time dependent, and this is the divergence of this y vector field, which is non-unique. It depends on a choice of horizontal cut. And this has to be a conformal Killing vector of the sphere in order for the symmetry, in order for the diffeomorphism to actually be a symmetry, and that's where this SL2C is coming from. So when T is an L equals 0 or L equal 1 spherical harmonic mode, those are global translations. Otherwise, these are the super translations that turn good cuts into bad cuts. That's just a description to remind you the description of the group. But my point was to show you why Komar gives you a bad formula, because now, bad flux balance law, because now you can compute actually, you can send Komar to Scry, you get some formula, the mass appears, so you're happy, the angular momentum appears, so you're also happy. actually the time derivative of the shear appears, and this is actually the news. So this is the content of gravitational waves. So the fact that it appears in the charge, you're a little bit less happy. And then when you compute the flux, you immediately see the problems with this choice. Because the flux, so let's say the time variation of the Komar form, it has a term that is proportional to the news, so it's 0 if there are no news, so that's good. It has a term that is proportional to m dot, so that's kind of cumbersome. But worse, it has a term that is proportional to the double divergence of the shear. F dot is just a boost, so this tells you that the boost charge that you obtain from Komar actually is not even conserved in Minkowski spacetime. It's enough to choose a bad cut, and then you will see a non-trivial conservation law, even though there's no flux or radiation waves whatsoever. So this is just to give you an idea that when you don't have killing symmetries, and here actually we have an asymptotic killing symmetry, so it's almost the best we can do, Komar flux balance law is not very useful. And the idea is, can we use these ambiguities to basically move terms around so that we get a flux balance law which is physically useful. So turn the ambiguities instead of a problem into an opportunity to get a better flux balance law. But before telling you how this is fixed, let me tell you the history, because this is not how people identified charges in the first place. The history, well, of course, this starts a long time ago. Bondi and Sachs already identified a momentum. The question was how to identify. So the charge associated with the global translations, already Bondi and Sachs had it, and in fact the Bondi energy loss formula refers to that. The question was how to attribute charges to super translations, and that question was answered in '77 by Geroch. He found that there is a unique supermomentum charges with a number of properties that you would like. In particular, it's general covariance, so it doesn't depend on any arbitrary structures, such as choices of foliations or choices of conformal factor, and vanishes in Minkowski at any cut of Scry, which is non-trivial because even in flat Minkowski you can have non-trivial shear, for what I was saying. Then a few years after, Ashtekal and Streubel identified a flux with a symplectic interpretation for all BMS symmetries, and they proved immediately that the nether charge, if you want, associated with this flux, or the potential of this flux, namely they proved that on shell the flux was closed, actually was exact, and that the potential of the flux for supertranslation was Geroch's supermomentum tensor. So it remained to just find the angular momentum charge, and then everything would be completed. But this was much harder. Well, harder anyways. And why it is hard? Well, because when I showed you that the vector field that you can split in translations and angular momentum, the problem is that this split is non-canonical. Translations and supertranslations are canonical. They correspond to an ideal of the BMS group, but Lorentz group, Solent subgroup, no. You have infinitely many different subgroups inside the BMS group. They all depend on a choice of cut of Scry. This is kind of analog to the fact that in flat spacetime, you might want to choose an origin before talking about angular momentum, whereas translations don't need that. But it gets worse because of the presence of gravitational radiation that forbids you from interpreting cuts of Scry as coming from a point in the bulk. So that's what technically made it more complicated. And in particular, super translations furthermore change the cross-section, because you remember the drawing I made. You do a translation, you have a cut like this, goes into a cut like that, but you do a super translation, a cut like this goes into one of these shearing cuts, if the initial one was not shearing, and therefore the algebra of the BMS group knows about this non-trivial mixing between changing cuts and super translations, which means that any charge that represents correctly the angular momentum as a moment map, so as a linear map between the vector fields and the phase space, must also have this complicated transformation law, in well, complicated, it's still linear, but these non-trivial, non-obvious transformation laws in which it picks up a supermomentum shift. Sorry, this should have been T prime, not F prime. And this property is hard to get right if you just, I mean, people have tried for more than 20 years to find a formula and didn't get it right. Side remark, there's a lot of research in the last few years on constructing things that are called super translation invariant angular momenta. That's a very interesting research direction, but for what I've said, it should be clear that any such construction can never represent a moment map, namely a linear representation of the symmetries in the phase space, because it has to be non-supertranslation invariant by definition. Okay, so the answer actually was very, very highly inspired by Penrose and the use of twistors. So in fact, in 82, Penrose proposed a formula based on two surface twistors, which the year after Paul Todd developed a little bit further and applied into study of quasi-local observables as well. And one more year after, Drey and Streubel provided an interpretation for this formula at Sky of a real Lorentzian spacetime. And then the next year, Drey proved that the flux of this formula actually is the Ashtekar-Streubel flux for a rotation, for any cut of Scry. So basically, at the end of the day, thanks to this, it was possible to identify a unique set of charges and fluxes with a certain number of properties. So let me talk a little bit about twistors, because as I'm trying to say, they actually really played an important role. It is often said that the angular momentum charge is the Drey and Streubel charge, but what they really did was to pick up this idea from Penrose, and now I'll come to Lionel's point, because actually Penrose made a very, very important observation that, so if you remove the trace, now we can actually remove the trace as you wanted to, you don't get comma here. Well, of course, it is always ambiguous what you get here up to another exact tree form, but anyways, he proved that actually if you have a Killing vector, the precise formula with t and not t minus the trace of t can be written in terms of the Riemann tensor contracted with some antisymmetric tensor S, where this tensor S is related to the Killing form and it satisfies this property. Now it's actually not so obvious how to, before coming here I was trying to see how to prove that. I gave it a shot. I was not able to prove it. However, if you look at Haggett and Todd's book, it says it is then a simple exercise to verify that, which made me feel a little bit like, can I say, uncomfortable. But then, even more interestingly, if you look at Penrose's original 82 paper, he actually says, via some non-obvious manipulations. So, I think the next week I'm gonna get around with those two and try to understand what these simple manipulations are. But anyways, so this equation here has an interpretation in terms of a symmetric two spinors, and actually you can prove that this defines, this is a twistor, this defines a two twistor. But of course, what do you do now if you don't have a Killing vector? Because we're interested, we already know the comma is good enough when you don't have, when you have isometries. Point is, what do you do when you don't have isometries? And Penrose had just this brilliant idea, well, you know what? I don't have this anymore, so just drop it. Well, let me keep that, okay? Now, okay, that's still not good enough because this equation is still over-constrained. So similar to the Killing equation, this does not admit solutions in general curved spacetimes. But the next brilliant idea was, why do I need to solve it in an arbitrary, as a tensorial equation in arbitrary spacetime? After all, I'm only interested in surface charges. So I'm only interested in solving this pull back on some two surface. And so this was the second brilliant idea, which was to say, let me actually impose, let me impose this equation only on a given two surface. And then it turns out that actually you can find solutions to this surface. In fact, you can even find most general solution. And this is what he called two surface twistors. Any solution of these two twistors can be written as a linear combination, as this binomial in different solutions of the standard twistor equation, which you want to solve only its pullback on a two surface. And if you pull it back to Scry, to a cut of Scry, these equations become some equations on the et of these two components expressed in terms of the two shears, transverse shear and the parallel shear at Scry. Yes?
So you said, what if you don't have a Killing vector? But do you still insist on this two twistor equation?
Yeah, exactly. But on a smaller version, not all of it, only its pullback on a given two surface.
But isn't it, if you do have this equation and you in vacuum, then you didn't know that you have a Killing vector, but you do have one, because if you drop the symmetrization, that would be a vector times epsilon and differentiate again, and you find that this vector is a killing vector.
But you are asking now that this equation is satisfied everywhere in space-time. Yes, we are not. We are only going to ask that this equation is satisfied on one surface. Just really one surface. In fact,
you get a small, you get a finite-dimensional solution space, and you could generate, in the situation you're describing, you could generate a solution that way, but you can't in general.
Absolutely. And in our case, well, in Paul's applications, these two surfaces, I guess it could have been anywhere, because there's a construction of quasi-local observables, which I'm not going to talk about. But in our case, we're only interested furthermore in the special case in which these two surfaces at scry, so it's just a cut of scry. And then we get the additional bonus that these equations simplify, because scry is shearless, shear-free, and so basically all you have to solve, you have a much simpler system of equations to solve, which in fact, it basically amounts to the fact that I mentioned earlier on, that the asymptotic killing vector fields are actually conformal killing vectors. So basically what you're solving here is the conformal killing equation for a cut of scry. So that's why it works. Actually, what I don't know...
The miracle is that instead of dealing with an overdetermined system in space-time, you have an elliptic equation.
Exactly. Yes, that's right. That's a mathematical miracle. The physical miracle is the fact that in BMS group, they have to be conformal killing vector fields. So not arbitrary vectors. So that's also important to find solutions to this equation. Okay, then basically the rest is just, I guess, simple exercise. I think Paul is trying to find the proof. So the rest, I think, is also some simple exercise in which basically you start from here, you have found this solution. So here, this is in GHP notation, so this is just a basis on scry. So this is a basis adapted to the cut you have taken on scry, and this omega 1 and omega 2 are the solutions of that previous equation. You are in vacuum, so there's only psi. So this equation up to numbers becomes equal to this, and then all you have to do is to basically plug in the solutions you have found. And what Penrose interpreted as was a definition of the angular momentum twistors in an asymptotically flat spacetime if we are at scry, or in an arbitrary spacetime, but as a notion of quasi-local observable. Now, what Drey and Straubel were able to do through cranking the integration by part machinery and using those various miraculous identities that Het satisfies, actually Penrose already knew this, that when you spatialize to a supertranslation, you get this expression, which was Garroch's expression for the time component of the supermomentum vector. But what they showed is that when you go through integration by parts and you use the fact that psi3 is at of the news, and therefore you can replace that with sigma dot and integrate by parts, you get rid of this piece and you end up with this. So that was, and then in their paper, they just basically proposed this as a charge, compare it with other proposals that have been in the literature, show that it had better behavior than the previous ones, but they did not yet know whether this charge was symplectic. Because you see, what's amazing is that also Penrose in this paper, he says, I actually have no idea what is the flux of this charge. So it looks interesting for various reasons. In fact, he actually basically credits you for many of the reasons why it's interesting, but it doesn't say, I don't even know whether it is conserved in non-radiative spacetimes, which is true. And that's what, in a very, again, tour de force of integration by parts and identities, Drey proved that actually this charge acts as the potential of the Hashtag-Straubel flux. So if I write the flux as a 3 form, really you have an identity, you use the Einstein's equations, is exact, and is the D of that structure. So that was really an important result. That meant that by 85, there was a complete characterization of charges for the BMS group with their fluxes. They were conformal invariant, Foliation independent, they had all the properties you might want. They were zero in Minkowski at any cut, and they were conserved in any non-radiative spacetimes. However, it took another 15 years before it was understood how to derive them using Nether's theorem. And that's because you had to solve these two problems of the ambiguities and the integrability. And the resolution to these problems is due to a paper by Wold and Zupas.
Well,
Yes?
There was a paper by myself and Neil Prandina, and in fact one by myself as well, 87 and 91, where we gave Noether's derivation of Penrose's quasi-local mass.
So it would be very nice, great, thank you. It would be very nice if we compare it with the one by Wold and Zupas I'm about to explain, so that we can see if it's the same or if it's a different one. That would be very
Well,
nice.
they may have done it better than I.
No, I don't know. Maybe you have done it better. No, I'm really sorry. I just don't know it. It would be great. Yeah, let's. Yeah, absolutely. No, with pleasure. Let's go through it and see. So let me tell you how they did it, and then we'll see. So, right. So let me just remind you that we said that the Noether current is basically given by hooking the symplectic potential with a transformation, like if you do in standard classical mechanics or in any global symmetry. The special thing of gauge symmetries is that it is actually proportional to the constraints of the theory. So on shell is 0 up to an exact form. And also that there is this cohomology equivalence class that tells you what are all the possible shifts that you can do. Because you see, you move from theta to theta bar, and of course, xi of delta and xi of d will give you non-trivial things which you might be tempted to move to the right-hand side and take them as part of the charge. So this is how you can play with ambiguity to make the flux balance law more physically useful. So Wold and Zupas said, okay, so what I want to do is to see if first I can get rid of the ambiguities, and second, get something that is physically viable. In particular, is the Ashtekar-Schreiber flux for BMS. The first criterion is stationarity. So we would like that the preferred symplectic potential actually vanishes on all non-radiative solutions, which was not the case with the Komar symplectic potential. Problem is, what do you mean by radiation even in GR? We don't have a characterization of radiative degrees of freedom locally everywhere in space-time. So typically, in order to be able to characterize what you mean by gravitational radiation, you do need some additional structures. For instance, at Scry, you do this by giving yourself a conformal factor, a compactification, and you give a foliation of Scry typically to introduce the shear. So you have lots of additional structures you need. Even if you think about Sachs constraint-free data, you will say, no, wait a second, I know what radiation means. I have Sachs constraint-free data. But those, you can only identify them if you do a certain gauge fixing. So you want your hypersurface to be null. You want to choose, like a Bondi type coordinate system. So that's also some background structure. You would like to have a null hypersurface, and you would like to describe it using a null vector with some properties. So typically, it's through the addition of non-dynamical structure that we can kind of like take those as benchmarks to then identify what we mean by radiation or not. And that makes it, so now these additional structure, you can think of them in terms of boundary conditions, or you can think of them in terms of universal structure. To a large extent, this is completely equivalent. I will say more about that. But the point is that now you have kind of polluted your beautiful, completely general covariant theory of gravity with structures which are not at all general covariant. They are backgrounds. They are not dynamical. And so the very important second requirement that Wold and Zupas added is that you need to make sure that this additional structure you've added does not percolate in your choice of symplectic potential. So you want that your symplectic potential is actually general covariant, namely does not depend on any of these choices. So that's the second requirement, the requirement of covariance, which you might say is trivial, which you do in GR. No, it's not trivial because we're doing GR with boundaries and boundary conditions or universal structures. And in fact, it's actually easy to see using the covariant phase space formalism that loss of covariance means that the field space and the space-time Lie derivatives don't match anymore. Because on dynamical fields, by definition, these two transformations are the same. But if you have a background field, it's constant in field space. So its Lie derivative in field space is 0. But being a field may not be invariant under Lie derivative. And therefore, there might be a discrepancy. And so this discrepancy, which can be called Laurent Freidel, I think, introduced the name of calling it the anomaly, even though it's just a classical property, is what it's like the smoking gun of background dependence. And now if your symmetry group is large enough that it can probe these dependence, then you can state covariance as the requirement that your symplectic potential satisfies this equation. This is what Walden-Zupas did, and the reason it works is that the BMS group changes the conformal factor, and the BMS group changes the foliation you're using. So it is large enough to test both conformal independence, conformal invariance and foliation independence of your choices. So that's the second requirement. Walden-Zupas added a third requirement, which is that they wanted, remember?
Sigma on the left hand, the second equation?
Sorry?
Condition 2, covariance.
Delta. So this is the Lie derivative in field space equal to the Lie derivative in space-time. Remember that this is a 1 form in field space and a 3 form in space-time. So you want this funny equation. But in fact, if you have a minute later, I can show you why it's very obvious that you would like this for background independence.
So again, you're treating psi there as depending on fields as well as depending on space-time?
Sorry?
The vector field psi is the vector field both in field space and on space.
Ah, no. If psi, okay, that's tricky. So if psi is field dependent, I claim that you still need to impose that equation, but the discussion becomes more subtle because there's an, so maybe we can have it later. If you have field-dependent gauge transformations, it's a little bit more complicated, but I still claim that this is the right condition you want, and not what is usually called the anomaly-free condition, which is an additional piece.
As far as the left-hand side of that equation goes, you can psi as a sort of constant vector.
Yes, absolutely, yes. Okay, now remember that in this cohomology class, this does not affect the symplectic 2 form, but this does. So actually, Walden-Zupas added a third requirement that they don't want to do that. They just want to stick with the standard naive, if you want, the symplectic structure that you can read from the Einstein-Hilbert action. And I'm going to call it condition 0, not 3, first of all, because they impose it as first, and second, because I actually would like to also relax it in some situations. It's actually known that this var theta in general is not trivial. Wald himself knew that the Einstein-Hilbert and ADM variables give symplectic structures which are different. They differ by a non-trivial theta, var theta. And I thought that I had also pointed it out for the difference between Plebanski and metric, but Jorg earlier on in the week showed me a paper he wrote in '92 with George, in which they already had, maybe not the most general case, but already had pointed out this difference. Okay, so once you have this criteria, then effectively Walden-Zupas proved that there's a unique set of charges, and actually they coincide with what I previously described. So that shows that they can also be understood as nether charges. We'll discuss with Lionel his other derivation of it. So some comments about these charges. So you can write them like this on a certain cut, and then you adapt the foliation so that this cut, for instance, can be a nu equal constant leaf of the foliation, and then they have this form here, and you see is psi1 and psi2, which are things that you might naturally think of using as charges, but they have these additional decorations that depend on the shear. And why is that? Well, in this derivation, it's kind of obvious that you need these additional derivations if you want that the flux is given by this. If you remove them, then the flux will have additional terms. It will not spoil their stationarity, but it will not be symplectic in the sense that it comes from just hooking this symplectic potential here. As I said, they have a number of very useful properties. Covariance in particular here means that they represent, they are a moment map, so they give you the right Poisson bracket, sorry, they give you the right bracket between vector fields. However, remember that the system is dissipative. In general, you might have radiations at your cut, so this current is non-zero. So what gives you the actual representation of the algebra is not the standard Poisson bracket, because there's no standard Poisson bracket in dissipative system, but is this standard action minus the flux, and this is something that Barnich and Trossard introduced, so this is often called the Barnich-Trossard bracket. So you can say that they realize the algebra either at a non-radiative cut or at a radiative cut through this Barnich-Trossard bracket. And actually it's very easy to prove that the fact that you realize the algebra, it is really a statement of psi is the only background field that these charges depend on. So if you satisfy this algebra, your charges are conformal invariant, Fourier invariant, and so on. On the other hand, if you don't satisfy the algebra, if you have some non-trivial co-cycles that are field dependent, I claim that that's typically a bad thing. It's typically a sign of the fact that your charges do depend on gauge fixing, conformal choices. So there's a lot of papers in the literature in which these co-cycles appear. And my understanding after this series of works is that one should try to get rid of them by selecting a better set of charges for your boundary symmetry using this Wald-Zupas procedure, if it's possible. Now, what is the relation with the canonical generators? So, as I said at the beginning, I'm going to be talking about partial Cauchy slices. So let's think about this. We have two hyperbolic slices that cut scry. So each of these sigma is like a partial Cauchy slice. It does not have all the full degrees of freedom of the theory, but it has a certain set. And because of the closure of the symplectic 2 form, you know that the symplectic 2 form here is equal to the sum of the symplectic 2 form here and there. So in a sense, you could say that all the information about solution that we know from here is split into information that goes there and information that goes there. You can further prove, as Abai did back in the day, that all the information that goes here is just radiative data, so that the Coulombic data stay as corner data of sigma and sigma prime. So that's why I used always to refer to these as the radiative phase space of GR. But anyway, these are like different Cauchy slices, so different partial slices, sorry, so different notions of phase spaces that you can think about. And now on sigma, the generator will give you this form. This is the Ayerwald famous formula. And so what you get is that the BMS charge, the charge, you can think of it as a generator, but only if your cut is non-radiative. Or if you're looking at a tangential psi, so like a rotation. In general, it will fail to be a generator if there is radiation. And on the other hand, if you look at the phase space here, then it's actually the flux that you can think of as the canonical generator. And in this case, there's actually an interesting additional feature, because again, you would say, it's only the canonical generator if the flux vanishes, so if there is no radiation initial final cut, otherwise you have this non-integrable piece, true. But the nice thing of the radiative phase space is that you actually know all the local degrees of freedom, so you can actually choose a norm, you can equip it, you can give it a topology by choosing some norm, and then you can show that radiation-free initial and final cut is a measure zero subset, so you can actually extend by continuity your generator in the full radiative phase space. So anyways, with these different cuts, you can think of either the charge as generator in some limited sense, or the flux as generator in a more complete sense, but we're talking about generators on different phase spaces. So now let me talk a little bit more about this var theta, which Wald and Zupas did not allow, and then they got a unique set of charges. So the balance law for supertranslations has this form, and famously it has a hard term and a soft term. This soft term, which is just linear in the news, is proportional, forget about this rho. Let's say that we take a round sphere at infinity, so forget about this rho. So it's proportional to the trace-free double derivative of t, the supertranslation parameter. So this is like the good cut operator. So all the zero modes of these operators, which are the L equals 0 and L equal 1 spherical harmonics, corresponds to the global translations in time and in space. And so you see that if you look at a future pointing global, this should be in time translation, so t equal 1 on a round sphere. If you don't have a round sphere, it's more complicated, but it doesn't matter. Then this term dies, and you have a purely hard flux, but more importantly, you have a monotonic flux, because it's in the news squared. And that's the famous result when Bondi said energy has to be dissipated physically by gravitational waves. That's what proves it, because you have something that is strictly monotonic, and therefore energy is necessarily being taken away from the system. So energy is really being dissipated. So when people say that the Bondi energy loss formula was one of the first historical proof that gravitational waves really exist, they refer to this, the fact that there was a clear statement of dissipation, monotonicity of the flux. However, maybe But one thing that I wanted to advertise is that this Bondi mass formula is actually something that you reconstruct in waveforms, but it's like a deduced quantity. And as a physicist, even though I'm speaking to an audience of mathematicians, when you talk about observables, we're not only interested in the fact that they have some mathematical properties, we're also interested in also actually how do you actually observe them? Like, do they come with an operational definition of how to observe them? And for the Bondi mass, it's really not obvious how to observe it because it's a global quantity. And the way you can do it is that there's a famous formula that I think dates back to Hawking, or maybe Newman and Penrose already had it, showing that the Bondi energy mass formula can be related to the product of the two null expansions. But in fact, thanks to the fall-off conditions, you can write in terms of just one expansion, of the incoming null geodesic. And so actually these you can use to invent a thought experiment to give an operational definition of mass. And this is a paper that we posted with a byte this week. And let me give you a funny anecdote. So we make this thought experiment, and then the referee comes back saying, please add a description of how you can realize your thought experiment in practice. So what do you answer to that? I mean, I guess the whole point of a thought experiment is that you cannot realize it in practice. Fair enough. That was a very good referee, I guess. So that's just like to say this.
Sorry, are you
yes.
saying that you got the referee report a day after posting?
No, the thing is that this paper was more than a year late in a collection of 60th birthday of Jorge Pullin. So we had to rush. It was in the summer, so we didn't post it. We went straight for all the other process. But usually we don't do that, but you have a point. Now though, Bondi, I don't know if he really said this, but he's often quoted with saying, if gravitational waves are real, you can actually heat water with them. Now, his formula though doesn't really tell you how you heat water with them, because his formula tells you what is the energy taken away by gravitational waves when you integrate a sphere that is over the whole universe, or anyway, around your isolated system. So about the bucket of water, it doesn't tell you much. And in fact, you even know that you won't know anything about the bucket of water from this formula, because suppose that you try to localize the charge by taking a t, which instead of being t equal 1, is a sharply picked function there where the bucket is. Then, sharply picked function has a spherical harmonic expansion with all higher multiples, and therefore he will pick up this term, which is not monotonic, and therefore the flux that is seen by your sharply picked t will not be monotonic. So you can decrease, so there's no way you can think of the supertranslation charges as localized energies. In fact, you relate them rather to these soft modes, you relate them to memory, you have another physical interpretation for them. But if you allow me to relax condition 0, now the symplectic potential that satisfies 1 and 2 is no more unique. You can find now a larger arena to play with, and in particular you can now ask, is there a vartheta such that we still preserve these two conditions, but now I get a purely hard flux for all supertranslations? And the answer is actually yes. And in fact, it's an interesting construction that goes back to the fact that, so if a late time you assume stationarity, then you have a notion of good cuts there, and your arbitrary shear that is tending to the stationary configuration will become hat of some bad cut in general. And in the celestial holography literature, this choice of bad cut is called the supertranslation Goldstone mode. Romain with Compere and Ferrucci, they call it the supertranslation field, but it's always this, a source for your shear in the stationary regime. And so if you give yourself this, now you can choose a symplectic potential and that satisfies 1, 2, and a purely hard flux. So with this choice, with this definition of charges, which are different than the usual one, of course, you will get, it will be possible to now, that quantity interpreted as the energy associated with a localized dissipation of energy on some bucket of water. So there are interesting things that you can do by extending the Walden-Zupas construction and allowing for this var theta. And in fact, even though Walden-Zupas used this construction to get the BMS charges, it has found since many, many more applications to Brown-New York quasi-local charges, to local horizons, to general null hypersurfaces, to the sitter, and in particular to style extensions of the BMS symmetries. And in particular, this very influential paper by Harlow and Wu, for instance, already to do that, just to obtain the quasi-local charges of Brown-New York, you need to go beyond assumption 0, and also in extensions of the BMS symmetry you need it. I don't have much time left, but I would like to just briefly, without details, just the basic sketch of what is this generalized angular momentum that people are interested in. So this BMS symmetry corresponds to a very clear and precise set of fall-off conditions on the metric, or if you want, very precise notion of universal structure. But there's been a lot of interest in the recent decade or so to consider more general, weaker fall-offs. In particular, this was spearheaded by Strominger and his infrared triangle in various gauge theories and gravity, with a lot of connections to physics, in particular to soft graviton and soft photons theorems and their subleading contributions. So there was a push to investigate whether weaker boundary conditions can also have interesting symmetry groups. And also it's very interesting because it sits at the crossroad of many different communities, Carolian geometries and Carolian fluids, celestial holography or flat holography, quasi-local observables. So there's various people that meet at other conferences. It's a little bit like these Twistor conferences, that there's people with very different backgrounds that meet but have some common best friend. There too, there's some interesting overlap, and so there's interest in developments. So this, let me just say, so if you are familiar with the boundary condition description of the BMS group, then you would say the normal is fixed, the affinity is fixed, the induced metric is fixed. If you prefer Garroch's or Penrose's universal structure description, you would say there is an equivalence class under conformal transformations of induced metric and null vector field that are common to all asymptotically flat metrics. These descriptions are equivalent. When you look for residual diffeomorphism compatible with these boundary conditions or isometries of this conformal class of fields, you get the same answer, the BMS group. And these weaker fall-off conditions that people have considered give rise to larger symmetry groups. Generalized BMS does not have conformal killing vectors, but arbitrary diffeomorphisms of the sphere. And you have also larger groups, and people are interested in these things for various reasons I mentioned. And so the question we wanted to ask about this generalized BMS group was whether you could also find a Walden-Zupas procedure for the generalized BMS group, because charges and fluxes had been proposed, but just looking at the stationarity condition, whether they were covariant, whether they came from a symplectic potential that is a Walden-Zupas type, this was not known. And in fact, unfortunately, the answer we found, so even though this group is very interesting, and so we were very motivated to find a positive answer, we found a negative answer, and the reason for that is that when you pull back the symplectic potential at scry, it diverges. So you need to use this cohomology freedom to also get rid of the divergences. And if you only look at the pullback of the symplectic potential, you can do it. But if you look at the full symplectic potential as a 3-form, then you can no longer do it. And so if a 3-form does not exist, only its pullback exists, you can expect that this gives problems with covariance, and this is actually what we found. So because I've run out of time, let me not tell you about what the proposal that we have to solve this problem is. Let me just give some conclusions. So first of all, two surface twistors have played a key role to complete the constructions of BMS charges and also offer a prescription for quasi-local charges, which I think is also very interesting to discuss, even though, of course, quasi-local charges don't have the nice canonical nature. So already charges, BMS charges sometimes are controversial, so you can imagine the quasi-local ones there's even much less agreement on what they should be. And I would like to advertise this procedure as a way to remove the ambiguities in the charges and the importance of background independence in the definition of the charges. And unfortunately, this procedure does not work when applied to the generalized BMS group. The way to make it work, I didn't have the time to go into the details, but is to keep the same group but change the way it acts so that boosts, because basically what goes wrong is that in the BMS and generalized BMS group, a boost, or the equivalent of a boost in the generalized BMS group, changes the conformal factor, and that's what creates problems. So you have to change the action of the symmetry group so that the conformal factor is not changed. And you can do that by restricting to just using round spheres at infinity, and so we call this the round Bondi sphere group. It has very interesting properties, this group, so if you have more questions, I'll be happy to tell you. And then I conclude with some open questions. That two surface twistor equation whose solution gave the conformal killing vectors was very useful for BMS. Can it also be useful for generalized BMS? This I don't know. Can one do better than what we did and restore full conformal invariance also for this generalized group? Another question comes from the recent work of Lionel, Romain, and collaborators, in which they actually have a covariant description of charges for a much larger group, and I would like to understand what is the relation with what we have found in full general relativity. And that was all. I would like to thank you. Maybe we'll see you at the next meeting, which maybe, if we motivate Maciek enough, well, this picture is low quality, I'm sorry, but this is the White Mountain. So if we motivate Maciek enough, maybe we might be able to do it there next time. Who knows? More barrels of wine for him, I think, will be needed. Thank you.
Simone, any questions? Any further questions? Yeah, Claude.
So the two-surface twistor equation generically has the right number of solutions, but if there's co-kernel, there actually are extra solutions. Is there, when you're out in infinity, is there a good gauge fixing condition that kills off these extra solutions?
Yes. Yes. We have to look again the Drey and Stover paper, or even the original paper. I think that's exactly what happens. Ascribe have exactly the right number of the maximum, the right number of solutions. Yes.
Yeah. And there's also a question of reality conditions, I guess.
Yeah, that's what Drey and Stover did. So in the original Penrose paper, not only he had no idea about the flux, he also was not too worried about the. I mean, he was worried, of course, but he didn't have an explanation, a resolution for the reality conditions. And that's also what Drey and Stover did. So they provided an interpretation for the formula in real Lorentzian spacetimes.
Just to, my memory of the detail then, Paul will know this better. Well, why don't you tell him what the story is? Because but I thought the story was that for the angular momentum, they could only identify a complex centre of mass, not a real one, even at scribe. But maybe you can say it authoritatively.
Sorry. Yes, I think that's the answer there. But yes, you couldn't get what you wanted from the angular momentum because part of what you wanted was the idea that it behaved appropriately under translations.
Super translations.
Well, that it...
That's the translation.
Yeah, but you wanted it to behave appropriately under translations, otherwise you didn't really know for sure that it was angular momentum. I mean, you've got a thing.
Yeah, but I mean, the fact that it behaves well under super translations gives you a more non-trivial test. But they had it.
You need a concept of centre of origin.
That's the
count.
But it was a complex, not a real one. So you got a concept of origin, but it was a complex one.
Absolutely. Yeah. No.
That was the story I remember.
That's right. That doesn't change. I see. That doesn't change.
Yeah.
So if you want, the origin will still be a complex origin.
I see.
But the formula itself, which is valid for both angular momentum and center of mass, so the boost charge, that formula is real through the analysis done by Drey and Streubel. And in fact, not only is real, it matches this metric expansion coefficient in Bondi coordinates that I'm calling J. and it's that. So the spin weight 1 projection of it is psi 1 plus that decoration on the shear.
Okay, that's it.